So that is the summarization of the GAT. Yeah, let me correct the typos here. So let me upload the corrected version to the iCampus. In the design space is recently published in the NeurIPS. So as you know, we have multiple choices for the aggregation, and we may consider different activation functions, and we may also consider different dropout rate in layer-wise normalization. So they proposed a design space by looking at the previous literature. So these ideas are actually from the neural network and the common techniques for the neural network, right? The aggregation ideas are from the GNN, but the previous achievement from the neural network could also apply for the GNN. So their basic idea is we can stack GNN layers. In the previous GCN, for example, we get the attribute and train multiple GCN layer and decide the final class label using the softmax layer, right? But it could be generalized and not generalized. So it could leverage the previous achievement of the neural network. For example, we can pre-process the input attribute. Instead of you directly using the feature vector, we can utilize in multiple the MMP layers, and we reduce the dimensionality before we aggregate by considering the neighbors, and then the GCN layer and the final output also could go through the post-process layer. And GNN layer also, instead of utilizing just linear transformation and activation aggregation, we can add the batch normalization and dropout in the GCN layer. So let me give you more details. So in the GCN layer, so in this case here, it could be composed of the multiple ideas. For example, in this linear transformation, we can normalize their output using the batch normalization and drop out the output, the randomly make the output the values as zeros, and we activate the value to utilize the nonlinear functionality. And the activation function choice could be from these ones. Could be, we have so many different activation functions these days, right? It could be more. And aggregation function, we considered so far the mean and sum and max. And maybe you may consider the LSTM and so on. So these are intra-layer design choices. And we also consider inter-layer design. So inter-layer means inter-GCN layer and inter-MLP layer, and in between MLP and GCGNN and GNN and MLP layer, something like that. So we consider the just stack the output, or we use the skip connection and skip sum and skip catch the alternatives. So let me also give you there some examples about this. So as you know, let me give you his in the following slides. And pre-processing layers. So here we also need to decide how many layers are gonna be used for the pre-processing, and how many GCN layers are used, or how many post-processing layers are used could be considered here. So these are the design choices. So design choice means, design space means these are possible options for your problem. So far, we had considered just simple node classification and link prediction, and mainly node classification, and simple citation data set and protein interaction. But depending on your own graph data set, for example, when you deal with sensor network data or just social network data, the Facebook or Instagram data, depending on the size of data in the group of the people in the data set, the proper choice in this space is entirely different. So you have to consider all the design choices, and you have to have the appropriate the selection. So these are summary. So in that paper, they considered, as far as I know, so many different the downstream tasks. So it is composed of 32 tasks, and they considered several alternatives. So particularly here, so we can combine multiple sets, right? Depending on choice of the batch normalization, dropout, value, mean, we can make many different combination, right? Batch normalization true and dropout false, and I would like to say in this case we have two choices, and three choices, and three choices, and three choices. These are possible number of the choices. So when we consider another interlayer design, so the possible number of choices increase it. So these are summary. Depending on the batch normalization, they try to see there exists a general recommendation. For the 32 downstream tasks, so batch normalization usually helped. So this graph represents the average ranking. So we have two choices with respect to batch normalization. So one is so we have two. So we have the rank 1, rank 2 information, and depending on choice of the batch normalization, we have multiple rankings, right? 1 or 2, and we averaged their average the ranking depending on the choice of batch normalization. The other choices vary, and this is just normalization. So just try to see the effect of batch normalization, and the others are just randomized equally. And when we use batch normalization, it is highly ranked compared to the the another case. So batch normalization helped. What about dropout? Surprisingly, so when we use zero dropout rate, which means we don't use dropout, it worked better in general, but not all not the all cases, but in general it dropout. The zero dropout rate worked well. So which means we aggregate all the possible choices. In that case, it worked better than ignoring some of them. So this is one of the surprising results. An activation p-value worked better. Aggregation function sum is better. In number of messaging passing layers, so this is the number of GCN and GNN layers, and 4, 6 are better, but we don't have general choice, so we have sort of a mixed opinion here. So far we have general preference. So in this case, true batch normalization was better, zero dropout rate was better, p-value was better, sum is better, but in this case we have mixed opinion, and distribution wise also difficult to conclude one choice. And layer connectivity wise, SkitCat is better. It is also what we consider pre-processing layers, difficult to choose the best number, and post-processing 2 is better. And batch size, we don't have the best option yet. And learning rate 0.01 is slightly better. Adam is better. In training epic 400 is better. So we have this amount of the design space. They get to try to summarize the result of 32 tasks. So this is the general guide. So depending on your own data set, you have to choose your best parameter. But this is just a guide, and you don't need to trust here's observation, but just make the reference and think about your best choice. So as you see in the previous summary, we have mixed opinion in the message passing layers experiment. It varies a lot depending on the downstream tasks and data sets. Why? What is the meaning of the number of the layers in GNNs? So because in particular, we have believed that the deep neural network are working better than the swallow neural networks, right? That's why we call the deep neural network and deep learning. But in this case, GNNs are not deep, right? Because often we observe 4 and 6. We're still observing some observation at the two message passing layers. Compared to the previous achievement For example, the image classification, the VGG, they have the CNN layers, and LastNet, they use up to 152 CNN layers. The text classification, 29 CNN layers. GPT-3, they have 96 attention layers. So by having more and more and deeper layers, we were able to get better performance in practice, but not in the GNN. So we have to understand what the number of the GNN, the messaging passing layer, means. So here is a visualization of the result of the one layer of the GNN and two layer of the GNN and three layers of the GNN. So yellow node represents node of interest. This is the target node. When it is connected, and we can visualize the node as red in here. So considering just one layer, we decide the representation of the yellow node just considering the red node. What about we have the two number of the GNN layers to decide? Here's this node representation. We considering the direct neighbor's neighbor. It's a representation, right? So this representation is from the previous layer, and the second layer we aggregate this representation to decide this target node's representation. So the number of the red nodes increased in this example, right? Because we consider neighbors of the red node here, and then the number of red nodes are increasing, and they increased right now. What about three nodes? Covered almost every node here, right? Almost everything. So in other words, the shared neighbors are quickly growing when we increase the number of hops. The shared neighbors are growing, which means it's likely to have same output because we aggregate the neighbors, right? The neighbors are used to decide the representation of the target node. But when we have more number of the shared neighbors, is likely to have a very similar representation. That is a problem. So in other words, two nodes are highly overlapped receptor fields, then their embeddings become highly similar. So this is the visualization from the GCN in Karate Club. Each color represents the class label. When we use just one layer, we get this. It's not bad, result. Two layers, still getting meaningful result. So, and the representation is the visualization from the GCN layer, and when we set the final output representation as 2, and then we can just directly visualize this, right? Anyway, when we have 3 GCN layers, it got worse with respect to the separation between the different colors, right? Compared to these twos, it got worse. 4 layers. It's difficult to decide decision boundary, right? 5, also difficult, and they are becoming very similar. So node embedding will be highly similar, and it is likely to suffer from the over smoothing problem. So to smooth it too much, and it got really similar. So this paper published to AAAI 2018 it is reporting the over smoothing problem when the number of the GCN layer increased. So in theory, a GCN layer is approximately the same as Laplacian smoothing graphics. So they proved the relation. So this is from the Laplacian smoothings, the effect of the Laplacian smoothing. So in the graphics, we render the input 3D image using the vertex and edge and color, right? So we can visualize the output, regional output as like this. Laplacian smoothing is basically just decide the future representation by considering the connected node and get the average, and then we get this. So mathematically it is very similar actually. So by having average and average and average, and we have donut like shape, looks better, but we lose some information compared to the raw data. We're getting in very similar in the graphics. This helps to get a better visualization, but when in this case, we're three steps of the Laplacian smoothing, and when we have 100 or 200 like Laplacian smoothing, it got exactly the representation and visualization. They lose all the geometric information. It's similar in the graph, the GCN. So when we have the very similar the node representation, it is not likely to help to get the better performance in the downstream tasks. So how to overcome the over smoothing problem? So first solution is to increase the expressive power within each GNN layer. So in the previous examples, so each transformation aggregation function one linear layer. So this means a GCN layer. So we can make aggregation and transformation become a deep network. So for the aggregation and transformation before the aggregation, we can add multiple MIP layers, and we can increase the expressive power, right? This is one of the simple solutions. And second solution is we add layers that do not pass messages. So we don't need to have the GNN layers. So that's why we considered the another combinations in the previous the design space. So it is also helps to avoid the over smoothing problem, and you can increase the expressive power as well. And another way is to add the skip connections. So this is from the previous RASNet paper, right? So RASNet paper, they employ more than 100 CNN layers. So to avoid the vanishing gradient problem, because by having deeper layer, the the gradient is difficult to propagate toward the very depth CNN layers. So to avoid that, they intentionally added the skip connections. So this is the example before we compute the final before we consider some neural network, for example CNN, and we make a skip connection and add the output, and we can still propagate the error gradient toward the previous layer. So this helps to mitigate the gradient vanishing problem. And same in the GCN. We add skip connections, and we can implement the skip connections using like a skip sum. Just we use the summaze the two different possible inputs. I mean input and output. Here this is input and this is output, and we can also concat and employ another neural network. This is called the skip concat.